Looks like we're recording. There we go. So, welcome back. We're going to talk about database joins. We already did database schemas and we did select statements. Now we're going to talk about joins with the database. So, the basic learning goals, we want to talk about joins, which means we need to introduce Cartesian product. We want to talk about inner joins, outer joins, and self joins, kind of our basic join types. And then I have from codinghorror.com a visual explanation of the different types of joins, which I think is actually probably worth 978 words, maybe not the full 1,000. So, as we already know, SQL is a relational language, so it allows us to describe relationships between sets. So you can think of a table as like a set of rows. And select statements, these create criteria or conditions that we can use to sort of collect elements out of the set and return it. Now, just to kind of review a basic select statement, we can say select star. The star here means all the columns from the actors table where the name is Christian Bale, because of course everybody loves the Batman movie. I guess I'm immediately dating these lectures, so if we use these same lectures in 10 years, people will be like, what? Christian Bale? But anyway, this will give us all columns of all rows where the name in the name column is Christian Bale. There's probably only one, but it's possible that there could be like future actors named Christian Bale. Now you can have more complex statements, so we want name and age from actors. Here we've got an alias as A. The word as here is optional. Sometimes you'll just see actors A. Doesn't matter. Where the name is not Tom Cruise and the age is greater than 37 and less than 51, and the number of Oscars is 7. I figured I'd draw a nice little sort of cookie picture here. So this is our set of actors. That condition, that actors above 37, that's creating a partition. So here on this side of this line, we're going to have, these are actors that are above 37, these are actors that are below 37. And then here we have actors below 51, that's another slice. So these are actors below 51, these are actors above 51. And then these are the ones, this is the intersection, these are the actors who are both above 37, because they're on the sort of north side of this line, and they're below 51 because they're on like the south side of this line. So these are the actors below 37, below 51 but above 37. So, simpler select statements, select star from directors. This will give us all the rows from the directors table, and it'll show us all the columns for each of those rows. Now, what about this? Suppose we say select star from directors, movie. So now we're selecting all the columns from two different tables. What is this going to do? We actually haven't really seen this before. Now, it's important to understand a simple example before we talk about more complicated examples. Suppose we have table A, it's got 3 elements in it, A, B, and C. So here we got table A, it's got 3 elements. Table B's only got 2 elements, 1 and 2. So we got 2 tables, A and B, we got 3 elements, we got 2 elements. If we say select star from A, B, in other words, select all the columns from one table, another table, this will actually create what's called a cross product, or cross join or Cartesian product. It's actually going to get all the columns from the two tables, this should actually say all the rows from the 2 tables paired up with each other. So this will trigger what's called a cross join, or sometimes cross product or Cartesian product. In other words, A cross B. So what does this look like? Well, A cross B, for those simple sets, we have to pair up everything in table A with everything in table B. So we'll have A1, B1, C1, and then we'll have A2, B2, C2. So that's everything we'll get. And then, of course, whatever columns are in A1, those will be listed first, then the columns in table B. So it's just going to pair everything up. And if we go back a couple slides, the cross product here, A needs to be paired with 1, B needs to be paired with 1, C needs to be paired with 1, A needs to be paired with 2, B with 2, C with 2, and so on. So that's essentially what this means. That's the cross product. Now, the full cross product, or cross join, It's actually not that useful. So if you think about directors in movies, the movie has a special foreign key column with the director ID, and the director ID, that's the primary key of the director's table. We don't actually want to pair every director with every movie. We actually only want to pair directors with the movies that they directed. So in other words, for our example, if, this is Avengers, and this is, what other movies I know that have been directed? Star Wars, and this is Indiana Jones, we don't want to pair Avengers with George Lucas and pair Avengers with Steven Spielberg. We only want to pair Star Wars with George Lucas, and see here, this is Indiana Jones with Steven Spielberg. We don't actually want to pair A up with anything at this point because we don't have the movies over here. So that's the idea. We don't actually want to pair everything up. We only want to pair up the stuff that makes sense. And so the way we do that is we do the join with some kind of a criteria. So select star from directors, inner join movies on directors, director ID equal movies dot director ID. So we're selecting all the columns from directors interjoined with movies, and then this on means, well, here we're creating a join criteria. We're saying, yeah, do this join, but only the ones where we've got the relationship we want, where the director's director ID matches the movie's director ID. So that's sort of filtering the result of this cross join. Now, I should mention inner join is the default join type. There's also an outer join we'll talk about shortly, but in SQL, especially in MySQL or MySQL, the database that we'll be using, and all other database implementations I've seen, which is pretty much just Postgres and a little tiny bit of Oracle, inner join is the default type. So if you don't say what type of join it is, the database system will just assume you meant inner join because the vast majority of times that's going to be true. There's actually a sort of simpler, more common syntax. So you can actually just say select star from directors, comma, movies, not actually list a join in here at all. And it'll just assume that, well, what you meant was an inner join. If you don't list a join type, it's going to assume it's an inner join. We're actually not using the word join in here at all. That's fine. And then instead of having to use the on clause, we can actually just say, well, where, directors.director ID equal movies.director ID. So we can actually just sort of make that one of the filtering criteria. Technically, this is not the correct theoretical syntax, but this is a very, very common implementation you'll see people writing, outside of database courses. You see a lot of programmers write it this way, and database optimizers, when they see this, they'll basically just understand that, well, you pretty much meant to write this, and that's what the optimizer will just do. So if you want to write things this way, you're welcome to. I certainly do, and it means the same thing. I should mention that this kind of join is called an equijoin, and the reason it's called equijoin is we're actually checking equality in this filtering criteria in this where clause. So that's going to make this an equijoin. There's other types of joins, like where you're joining on less than, or joining on not equal, or joining on string matching, and other kinds of joins, and those all have different names. But just for our introductory type stuff here, we're going to just focus on equijoins, because that's I don't want to say it's the most common because I don't know that for sure, but I would imagine it's the most common. So here we go. So here we've got select star from directors, inner join movies on, here's the join criteria, and select star from directors, comma, movies, using this with a where clause. This means the same as that. These mean the same thing. They'll be translated the same way by the database system when it sees these queries. They'll probably be optimized the same way because these are simple queries, although for more complicated queries, explicitly specifying the type of join and what criteria you want to join on, and then potentially trying to specify the order of the joins, especially if you're mixing inner and outer joins. A lot of times you have to get more sophisticated with your syntax. But for basic equijoins, where it's very clear what you mean. You know, anybody that looks at this is like, well, directors and movies, you only want the directors that directed the movies. There's a very simple primary key foreign key relationship. It's an equijoin. These are going to mean exactly the same thing. So there's a question, what is a join doing? You can think of it as the cross product, which is the basis of all inner joins. It's going to produce all the possible pairings of elements, and then it's going to filter them. There's actually different algorithms that implement how a join happens. The simplest thing is just to sort of join everything and then start filtering. There's other possibilities as well to kind of try to filter things early, especially if there's multiple joins, and trying to figure out what the right order to do multiple joins is in. There's going to be different performance characteristics. It's going to matter a lot what columns are indexed, but we're not really going to cover indexes in this lecture, possibly not even in CS262, but there's a lot more detail about this in CS320. We'll talk more about indexing. Now, you may want to join more than two tables. So we may want to get all actors in the movies they're in. And if you remember, the way we want to associate actors in movies is using a many-to-many table, because each movie can have many actors and each actor can be in many movies. So that would look like this. I want to select all the columns from the actors, movies, and actors in movies, and then we've got this where clause. Table A's actor ID matches the actor in movie table's actor ID, and the actor in movies table movie ID matches the movie table's movie ID. So we've got an equijoin here, we've got an equijoin here. And so this is sort of two equijoins because we're selecting from three tables. In order not to have one of these explode into a cross join, anytime you're selecting from three different tables, you have to have two equijoins joining all those tables together. Otherwise, you end up with a cross join, which is almost certainly not what you want. And so I'm not going to use the board. I'll just go ahead and put this into a slide. So if we've got, here's our list of movies, here's our list of actors, and then here's our actors in movies table. What this is, I've sort of basically drawn out kind of what's happening with this join. You know, Avengers sort of, it's got represented three different times here. Oh, I've got an error in here. Damn it. Yeah, I do. I got some extra stuff in here. Well, how about this? Figure out what's wrong about this. Because there's definitely an error in here. Maybe we'll make that the Moodle question for this thing. So that's basically what we're doing. We're joining the movies ID in the movies table with the actors in movies movie table, and then we're joining the actors in movies actor ID with the ID of the actors table. So that's basically what we're doing. And so that'll kind of give us the relationship that we want. It'll only match up the movie Avengers with actors that were actually in the movie Avengers, which includes, at this point, Robert Downey Jr., Scarlett Johansson. You can sort of see the error here. This row is in there twice. That's not actually supposed to be there. I need to delete one of those for this to be correct. And I actually need to take this Robert Downey Jr. He was supposed to be in Iron Man 2, so that actually should be kind of pointing here. So I got an extra row, and I've got this, I've got a pointer going to the wrong place. So that's actually what the error for this is. Cool. Oh, no, wait, I guess this is here. So this needs to be pointing here, and this needs to go. Cool. But that's the point of the join. You're sort of joining this with this, and this with this, which kind of lets us associate movies with the actors that are in the movies using this table. It's actually a very, very powerful technique. So some notes, you may actually want to restrict what columns are returned and sort of avoid that actors in movies or aim table altogether, because it's not really useful to view that. It doesn't have any information in it. It's just associating things. So you can go ahead and say, well, select a.name and m.title. Maybe we just want the actor's name and the movie's title. Now, the from clause and the where clause is all the same. We're just sort of restricting the columns. A lot of times you'll need to do things like this in order not to return all these extraneous columns that you don't really need to see. So now imagine this database. So we've got the employees table, we've got the departments table, and so we're just going to have the last name of the employee, the department ID that they're working in, then for the departments table, the department ID, and then the department name. This example, by the way, is ripped straight from Wikipedia, which has very good coverage of SQL joins. And note, you'd normally also have an ID, some sort of primary key that's going to represent these rows. We're just going to use the person's name as a shorthand. You wouldn't do that in practice, but this example is not actually about that. This is sort of the minimum amount of information we need to make this example work. So suppose we want to select all employees in their department. So this is our table here. If we do this just with an inner join, select everything from the department's D, the employee's E, where D's department ID matches E's department ID, what information is going to be missing? I'll give you a chance to think about that. So John has no department. So this null doesn't match any of these IDs, so that's not going to be there. Marketing has no employees. If you note, we've got marketing, that's department ID 35. Nobody's in the marketing department. So this inner join will work because it's looking for equijoin, places where the department ID is in fact equal to the department ID across these two tables, but it's going to leave stuff out. We're not going to know that John has no department. We're not going to know marketing's got no employees. So we can actually perform what's called an outer join. So we'd select star from employee, and since outer join is not an inner join, it's not the default join, we actually have to say outer join. And in this case, we're going to do left outer join. So we're going to left outer join employee with department on matching up the department IDs. So if we sort of do that, here's what it's going to look like. So this is our query to do our left outer join. We're joining on the department IDs that should match. Since it's a left outer join and we're listing employee first, that means we want every employee even if they don't match. Just go ahead and match them to null. And so if you look down here at the results, we're going to get the last name, the department ID, department name, and department ID. Now John, his department ID was null, which means he's not going to match a department, so it's just going to sort of fill those in as null, but at least we'll know about him. Whereas with the inner join, because this is null, we're not actually going to know that he's in no department. It's just going to give us the ones that do match, which isn't necessarily what we want, or it may not be what we want. Now, if you can do a left outer join, obviously you can do a right outer join. If we do the exact same query but with a right outer join, that means we want every department in there, even if that department has no employees. So if we do that, we'll actually get essentially the same results where we've got all of the employees matched up with their corresponding departments, but now we'll also get the marketing department, except it's matched up with null because marketing has no employees. Now, since we can do a left and a right outer join, you can also do what's called a full outer join. This means I want to see everything from both tables, even if it doesn't match anything. So we get essentially the same set of results, but with both of those things in there. John has no department, but he's still going to be in there, just matched to null. Marketing has no employees, but it's still going to be in there, except matched to null. So that's our difference between left outer join, right outer join, and full outer join. And remember, for these, you have to explicitly say that it's an outer join, the type of outer join it is, and what the criteria you're joining on. In other words, what columns you're going to be checking for equality or for whatever else you're checking them for in order to run that query. So I want to note that all of that is on Wikipedia, and it's a pretty good set of examples. It's a very simple example, but there's a little more information if you want to go check it out. It's also possible to have what's called a self-join. We may want to select all actors with the same name. Maybe there's two Tom Cruises. There's Tom Cruise, maybe there's like, I don't know, Tom Cruise Jr. or something like that. They're both named Tom Cruise. So the way we do this would say select A1.star, A2.star from actors A1, comma actors A2, where the names of the two things are equal. Now, in order for this self-join to work, we actually have to use the ability to sort of give an alias for things. If we just said from actors, comma actors, we couldn't have any criteria down here because it would be ambiguous. If we said name equal name, it wouldn't know which name you meant. So we actually have to use these aliases here in order to go ahead and get this to work. And so note, we're joining the actors table with itself. So an open question. What might go wrong? What's going to be wrong with this? Well, if you think back to prologue, something that was wrong with prologue is also kind of going to be wrong with this. If you remember with prologue, the siblings relationship, we said, okay, well, if x and y are siblings, there's some parent z that's a parent of x, and z is also a parent of y. But we also had to say x is not equal y. Otherwise, everyone would be their own sibling, because, if Bob is Bob's sibling, because Alice is Bob's parent, and Alice is Bob's parent, if we don't say that x and y can't be equal. So we kind of have the same issue here. This will say, well, Tom Cruise has the same name as Tom Cruise, but there may only be one Tom Cruise in the database. This isn't really going to know the difference. So how to fix this? Well, we could put in a criteria to take into account their actor IDs. Because remember, actor ID, that's the primary key. That must be unique. Primary keys always have to be unique in a database. So we could say, well, these can't be the same. Now, something subtle still could go wrong. This means you'd probably get it in both directions. You'd get, A1 would first be Tom Cruise with actor ID 5, and then A2 would be Tom Cruise with actor ID 17. And then you get it the other way. You'd get Tom Cruise with 17, Tom Cruise with 5. Actually, now that I think of it, that should be a period. I hope that isn't wrong everywhere. So an easy way to fix that is just declare some ordering. So if there's two actors with the same name but different actor IDs, just sort of do the select, but have the first actor ID be greater than the second actor ID. Doesn't actually matter. You could say A2 greater than A1. You could do whatever you want as long as it's greater than or less than, because what this just enforces some sort of total ordering. We don't actually really care what order they're in. We just care that we know that there's people in there with the same name. And so that's a little bit about self-joins. Now, I want to do a visual explanation of joins. So this is a simple example from this website, Coding Horror, codinghorror.com. This is from 2007. Wow, this is quite old. So suppose we've got ID and then name, pirate, monkey, ninja, spaghetti, and another table with the IDs 1 through 4, and rutabaga, pirate, Darth Vader, ninja. And so we can join these in different ways to get some interesting things. So if we just sort of do a straight inner join A to B on having the names the same, well, that's kind of your standard join. We've got A, we've got B, but we only want some certain things that intersect where the names are the same. So that's your basic inner join. Now, the opposite of that is a full outer join, where we're doing this on table A.name equal table B.name. Well, if we start lining stuff up like that, pirate matches up with pirate, monkey is in this first table but is not in this second table. So that's going to have to match up with null. Ninja's in both tables. Spaghetti's in this table, it's not in that table, and then same with rutabaga and Darth Vader. They're in the second table but not in the first table. So what we're doing is we're kind of getting everything. So we want not only the intersection, but also everything in A that's not in B, and everything in B that's not in A. This is sort of like a proper merging of the sets, or unioning, or whatever it is. Now, of course, a left outer join means we want the inner join stuff, but also stuff that's just in A, but we'll map it to null. And then we can actually do another slight variation. It's a left outer join, but we don't want the one. We only want the ones where table B is actually null. So this will just give us the things that are in A, but not in B, and also not in both. So this is the stuff that's uniquely in A, not also in B. Similarly here, if we sort of do the full outer join, but then check only the things that are null on both sides, that'll give the stuff that are uniquely in A and uniquely in B, but sort of not in the intersection of those. And then, of course, the cross join can't really be expressed as a Venn diagram. So this gives you kind of a really, I think, nice, understandable visual explanation of what's going on with these types of joins. And I believe that's all we have. Yeah, we're up to the clicker questions, which I'm going to move into the material for class on whatever day we get to it. Awesome. Thanks for listening.